So our next speaker is Dr. Ed Hall, and Ed is a ecologist here at Colorado State University, a research scientist who works on issues of microbial and ecosystem ecology. We're fortunate to have Ed here, and he's going to talk about the future of large lakes, the challenges of developing and maintaining sustainable watersheds. So, Ed, you're cut off there at the top. I'm not sure. I don't think that can be fixed, but if you would, so take it away, Ed, please.
Is this, is the audio on okay? Okay, so thanks very much for inviting me. Thanks to Galway and to Glenn for organizing it. And also I had to move up in the schedule because I have to leave a little early, so I apologize for that. But if any of this is interesting, please send me an email. We'll start a conversation on these topics. As we all know, freshwater, superficial freshwater, is absolutely essential for all human society. We're pegged to it, and this graph illustrates that in a really dramatic way. So this is population density, so people per square kilometer, and this is distance from standing water, from surface water. And you can see that the density goes from about 200 people per square kilometer down to under 100. And then these curves show the proportion of a population and their distance to water. So in equatorial, temperate, and cold regions of the planet, 90% of the population lives within 4 kilometers of standing fresh water. In arid regions, that stretches out to about 10%, 10 kilometers from standing fresh water. The fresh water is only about 2.5% of all the water on the planet, so a very small portion. But freshwater, or lakes and rivers, are even a smaller fraction of that. So they're 0.3% of that 2.5%. So imagine we took all the water on the planet and had 100 liters. The water that sustains our societies is less than half a teaspoon. Okay, and so what we're living on, what we're maintaining ourselves on, what's absolutely necessary as we add another 2 billion people to the planet in the coming 20, 30, 40 years is this teeny amount of fresh water. And furthermore, 90%, 95% of that fresh water at any given moment is in lakes. Here's a distribution frequency of lakes with their size. So most lakes are very, very small. But when we look at cumulative surface area, we don't come close to 100% or the total cumulative surface area till we get these really large lakes into the figure. So it's a very small amount of water that we absolutely depend on, and it's located in these really unique ecosystems across the planet. And we know the name of a lot of these ecosystems. So the Caspian Sea and the Black Sea are actually saline, but if we look at all the other ones, we know the biggest lake by volume, Lake Baikal in Siberia. Here's the biggest lake by area, Lake Superior, which is one of the Laurentian Great Lakes. Here are the other Laurentian Great Lakes. Here's the Aral Sea. That's what it looks like today. That's a topic for a whole nother talk. It's a very, very scary thing that's happening globally. And then there's some other lakes. George Clooney's lake, Lake Como. Other famous lakes are here on the map. But the point is, if we sum up the top 15 largest by volume lakes, we can account for 62% of all the water, fresh water, on the planet, surface water. That's just 15 lakes. That's like a fat baker's dozen of lakes. If we add another 20 or so lakes, we can get almost to 85% of total surface water. So we're talking about very few number of ecosystems globally that are absolutely essential for our everything we do, economic, social, cultural, and just our own livelihoods, including our own physiology. So I don't know how these images are going to come out because it's pretty bright in here, but we'll see how it goes. All of these lakes, not just the big ones, are under assault. And this is not really news, but there is a resurgence in the last 5 years or so that eutrophication, cultural eutrophication, is becoming a really large problem. So here is Lake Erie, one of the Laurentian Great Lakes from space, and this green outline is an algal bloom, absolutely massive proliferation of surface algae. Here is Warren Lake, which is about 1.5 miles south of this building in Fort Collins. And I got a call last fall, and they said, we're having these prolific algal blooms. What can we do about it? So here's the lake. It's surrounded by houses, and here's one of these intense algal blooms. Here's Lake Taihu in China, a little bit east of Shanghai, that unfortunately has sort of become the poster child for cultural eutrophication, but really intense. This is the wake of the boat, and if you can see this in good color, it's like thick, soupy algal bloom. And here's a moving water ecosystem, a river in Florida, St. John's, with these really pronounced blooms. And this is a really nice review actually on cyanobacteria, which is one of the most common type of bloom-forming organisms. And there's no mystery to what's causing it. It's phosphorus. There are a lot of things that could go into a bloom, but it's basically phosphorus, and it's from increasing use in the watershed and in the lake itself. And it's not, as I pointed out, it's not unique to any region of the planet, but in the last 5 years, it sort of came back. It was in the 60s we had a lot of problem. Lake Erie caught on fire. We did some mitigation, it became clearer, but now we're seeing more and more blooms. Every time I go to a meeting, there's more and more sessions on eutrophication and how to handle it. So I want to talk about one lake I've been working on for about 10 years, intermittently and sort of intensively for the last 2 years, and that's Lake Yohoa, seen here in Honduras. Here's the Caribbean Ocean. Honduras sits just north of Nicaragua and a little bit to the east of Guatemala, and Yohoa is sort of dead center of the country. And culturally, it's a really important lake. There have been continuous populations there for 4,500 years. You can see about, in a given year, 450 of the about 900 bird species from North America at Lake Yohoa throughout the year, so major habitat for wildlife. Really important fishery for local people who fish artisanally, means they just fish, they don't grow it in pens. There's also a really large aquaculture operation in Lake Yohoa that I'll talk about a little bit more. So it has all these uses, and the watershed's not very populated, just 100,000 people, but it's really important. And like all these other lakes I mentioned, Yohoa is going under a really pronounced eutrophication. So we were able to acquire data from the 80s, luckily, which is really hard to come by, from Lake Yohoa that shows that the nitrogen concentration in the lake is going up. This is data I've collected since I've been working on it. The phosphorus concentration is going up. And as a result, you're getting a decrease in clarity. So here's a 4 meters Secchi depth. It's a way that we measure clarity in standing water ecosystems. And it's down to about 1 to 2 meters any given time of the year. And so it's decreasing at about 10 centimeters a year. So what this means that in the next 10 or 20 years, Lake Yohoa will have a permanent algal bloom, much like parts of some bays, Meliang Bay and Taihu, permanently algal covered. And so this is the future of the lake. So in the last 2 years, I've been working with the fish farm in the lake that I mentioned and a local nonprofit on how can we address this problem. So the fish farm is our best guess at the main source of inputs to this lake. It floats in the middle. They farm about 4 hectares of the 8 hectares in the lake, and they pull out 77,000 kilos of fish every day. That's a lot of fish. It's only 20% of their operation in Honduras, and Honduras is a smaller of their 2 operations, with Indonesia being a more productive, they have larger operations in Indonesia. And so if we look at, thanks for dimming the lights a little bit, I'm just going to describe it to you because you can't see it. But here's a helicopter image that we took earlier this year. These are the floating pins, and you can see a little bit, I think, right here, some of the algal blooms. And then this is actually from Google Earth, so a satellite image where you can see the trails of algae leaving the fish pins. And I'm guessing nobody can see this, but there's that about the size of the pointer is a single set of these 4 fish pins. There's about 20 of them there. And there's an algal footprint that covers about 15 kilometers and covers the lake. So there's pretty good indicators that this operation is a main source of nutrients to the lake. Well, this company is quite fantastic. They helped fund some of this research, and they also provided us with all their data. And as you can imagine, any good business, they have fantastic data. So they told us exactly how much food was going in the lake and the percent of nitrogen and phosphorus of that food. And they told us exactly how much fish they were pulling out of the lake and the percent of nitrogen and phosphorus of the fish. And so I'm working with an undergraduate here at Colorado State, Gemma Fadden, who's a member of the honors program, a really fantastic student. And in the last 2 months, she's worked on these numbers, and we can report these really what I think are sort of first-time looks at aquacultural impacts on a system of this size. So the basic paradigm of the day is you can't eutrophy a large lake with a little fish operation. What we could show in 2005 by sampling the 7 major inflows with these labels shown here, we're sampled twice a month for flow and nutrient concentration, and we could compare that to these really unique numbers that we have on the aquaculture operation. So in 2005, about 2/3 of the nitrogen load to the lake was from the aquaculture, and a little bit under half of the phosphorus load. So that's pretty straightforward. This operation is putting unprecedented strain on the ecosystem. It's resulting in eutrophication and causing its sort of decline or lack of health, if you will. However, for one of these drainages, Rio Eyre, we were able to look at loading of phosphorus from 1980, 2005, and 2013. And so this is a log plot. And so what we've seen, if these numbers are right, that the increase in loading from the watershed is dramatic. We also have numbers from aquaculture, which is going down by about 2% over that period. And so it's really not that simple. We thought we nailed it. This is obviously 10 years ago. When we look at more contemporary data and we're continuing to work through some of these other drainages, it's clear that land use change in the catchment is really, could be driving some of this. And so now we don't know. Now that's a much harder problem because we know what the problem is. We know it's phosphorus and we know it's due to human activity. But when is it happening? Where is it happening? And how can you get those numbers? So in the US, we're really lucky to have the US Geological Survey that looks at discharge all over the country and monitors it regularly, nonstop with government funding and nutrient content. And so we can look at that data for a well-networked system. In most of the world, none of that data exists. And what can happen, especially in tropical systems, is a lot can happen in 1 or 2. You get a big storm event and a big transport of nutrients. And if you miss that, if that's not one of your sampling days, you have no idea the quantity of that loading. So here at CSU, I've been working with another NREL research scientist named Greg Newman. Greg Newman has developed this fantastic CyberInfrastructure product, which is to say it's a platform for stakeholders, people that live in the watershed, to sample and contribute their data to the website. And so we coordinate that activity through a school group or a church group or the nonprofit that I work with. And when there's a storm, instead of having paid researchers living in a tent by the stream, one of the stakeholders can walk out, collect a sample. We have some of the streams gauged, and so they can just mark the stage so that right there we can get a loading of these main events. And this really accomplishes 2 goals that you couldn't do just from a research perspective. It gives you exceptional temporal coverage and spatial coverage that you could never get you could get for an incredible cost paying researchers to get it. But it also gets the participants, the people who are using the watershed and impacting the lake, to have an investment and understand how this nutrients move through the watershed. So we think, and this is something we're just setting up, that we think that by using what's referred to as citizen science, that is people involved to help us collect the data, we can also help disseminate how these activities that you may not think if you add nutrients to your coffee plantation a kilometer or so from the lake that it has any impact on the lake. But as you contribute to this platform, you can download, you can look at nutrient loading over time, both in the lake and out of the lake, and in any given stream. And we think that this is a way to at once create coverage and monitoring and sort of broaden our understanding of how watershed practices work to the people that are impacting it. So just to speak briefly on a couple of these lakes in China, well, we're not alone in this system, so I plotted some of the lakes that I just showed. So here's, unfortunately, Lake Yehoa. Did this last night. I was quite disappointed. It's smaller than the laser pointer. It's really a magnificent lake. You just have to take my word. Taihu is about a 1/5 of the size, or maybe a 1/10 of the size of Lake Michigan. Lake Dianchi, which I think, let's see, is shown here. This is a really impressive algal bloom, and it's been having some of the same problems as all these other lakes around the world. And then this last September, a group of us were lucky enough to visit Lake Eyre by Dali City. And so each of these lakes, these Chinese lakes, are undergoing the same problem, which is obviously common throughout the world, as I've been saying. And I think what's interesting about Lake Eyre is it experienced a really dramatic shift in 2002. So this is unpublished data from Yang Xiao, who's at Central China Normal University and who we've been communicating with since our visit. And he was willing to share these data with me, but he showed these to us on our visit. So here's water clarity. It's pretty consistent from 1992 all the way up until 2002 at about 4 meters. That means that you can drop something in the water and see about 4 meters down. And then in 2 years, you get this dramatic shift. And this is a really common, this is referred to as alternative stable state. So it's a really common principle in lake ecology. And you see Eyre undergoing this shift. And then it's pretty steady again through there. And that's accompanied by an increase in phosphorus, shown over the same period here, and then a little bit later increase in nitrogen. And so what's causing these blooms is not the mystery, but where and when the nutrients are entering the system is hard to understand. So which practices? Is it during the rainy season? Is it during the dry season? Is it right after harvest? Is it right before harvest? If we could identify temporally and spatially where the nutrients are coming from, then you can start to talk about a sustainable mitigation pathway. So I want to just point out one great opportunity for Eyre that we noticed while we were there. There's this, the city of, I think, I didn't point this out here, but Taihu has 3 large cities right on its shores, which I'm sure many of you know, about 20 million people. Lake Dianchi has 1 city really close by, about 6.5 million people. And Dali City is only about 500,000 people, small village, I would imagine, by these standards. But the sewage from Dali City is actually pumped out of the watershed, and so it isn't the primary contributing factor to this eutrophication. So when we toured the lake briefly, there were these really fascinating irrigation plots. So here, which you can barely see, is an aqueduct. So there's water pumped from the lake and then moved inland about 1 kilometer or so, and then it makes its way back through these series of farm plots that are controlled just by handheld drainage ditches that flood irrigate the fields and then collect the nutrients and then deliver them to the lake. But these fields are farmed by stakeholders, also known as people, who live in the watershed. And it creates this great opportunity for citizen science or a monitoring program that puts the power in the hands of the people who are impacting the lake and that type of application that we're taking in Yehoah. So compared to the Lake Yehoah ecosystem, where there's this really complicated watershed with very little monitoring or management, there's shade-grown coffee here, an African palm there, and a chicken farm there, and it's really diffuse. Here you have a very highly organized system delivering nutrients to the lake that could be easily monitored through something like a citizen science program. So just to wrap up that little pitch for our current problem, and one way to meet it is it's clear that in the last 5 years we've re-entered this stage of eutrophication being a primary problem for these essential and few ecosystems. And the challenge really becomes over this next 50 years as we go to maximum population size globally, how are we going to increase use of the watershed and the lakes without ruining the ecosystem services that they already provide? And what we're working on here with Greg and myself and some other people is establishing a bit of a monitoring network that both at the same time increases our coverage but explains to people impacting the ecosystem how that's happening. So thank you very much. And if there's time for questions, I would take
Good.
1 or 2.
All right, thank you, Ed. Let's thank Ed, please. Sunjin, come on. So while we're changing out the slides and the mics, Ed, if you want to pull the mic and give it to Dr. Jen. Any questions for Dr. Hall? Yes.
So the question was, in the watershed monitoring, how are the citizens performing like the water chemistry analysis, for example? So the way we've set it up in Yehoah is things like temperature, conductivity, dissolved oxygen can be done right in place with point measurements. Chemical analysis are collected or delivered by the organization, so either our nonprofit, and then we run those at a local university. So the kits tend to be really low resolution and maybe perform poorly for these types of analysis. So there needs to be some baseline funding for that. But for things like stage and discharge, we can do that just by by point observation. What's that? Yeah, right. So what we do is we come into the system, we let them help design the study, you know, when and where they think the problems are, and then we talk about how to, you know, provide vials to collect water samples, how to monitor, how to freeze it, deliver it to us, stuff like that. Yeah. Yeah.
Okay, thanks.